very snazzy. Pelton Wheel Kentucky mine, I think it's a mine in California, gold rush type place. And this is just a Pelton wheel, exactly as we saw the other day, the little eBay model or Etsy model spinning on a board with an air jet. This looks like it's fed by a jet underneath the boards coming horizontally, so it would be an undershot wheel rather than overshot wheel by terminology. And I don't know what this is for. You could generate power for it, but I think this is pre-electrical power. No, it's got a generator on the side of it. And of course the generator is just an electric motor running in reverse, not reverse, but being turned and generating electricity by putting coil through magnets as opposed to electricity going in and it being turned. Yeah, so it looks like it's actually looks like it's a stamp mill. Yeah. So this is running, breaking up ore at a mine. They said it's a mine. So it just lifts these heavy weights and they drop down on the ore as it comes down through this thing. And you comminute it, you reduce its size, and then do something else with it to process it somehow. So a very mining related deal. What else? Jetlev you've seen. So we won't do that again. We know it's 28 grand. And we know how it works with this umbilical. We'll do an example with this, as we've done before when we talked about Bernoulli, maybe one of the online classes during the 5th week. So we won't do that. There was a very interesting thing in New Zealand that I got a copyright strike for many years ago. You're allowed 3 in 3 months or 6 months, and then they dissolve your YouTube account. I've never quite got there. A guy in New Zealand made a little hydroelectric thing with taking water that came down a stream. New Zealand's quite a steep country, a lot of elevation gain or loss, and he fed it into a motor from a washing machine as a generator and put it through a turbine and was generating power for it just from the water coming through his own land, which I thought was kind of curious. Monitors, I don't know why they're called monitors, but like the Kentucky mine, this is probably in Northern California, in the Sierras. Sierra, I guess, is plural of Sierra, self-plural. And this is alluvial mining for gold. The 49ers, San Francisco 49ers is the gold rush of 1849. And this is all eroded from the Sierra, deposited as an alluvial deposit in a river to quite high depths. In places like Grass Valley, these slopes stand very vertical, but they're just sand. And a monitor is just to wash it away and then process it. I guess the interesting thing about the monitor is that it has a curve in it. And I don't know, at the beginning, perhaps you can see it. Maybe there, yeah. You see it comes up and it has a right angle and a right angle and a right angle. And I think that's to allow it to be more easily held. And we'll talk about the forces that would act on something like that today. And then I found this just came up. I thought this is interesting as well. Just to make the point that the things we're talking about are the same as propulsion. The Jetlev is no different from this, except for a rocket, obviously the stream that comes out of the back of it is a gaseous stream, not a liquid. And I guess the other important thing to note is that it doesn't actually have to impinge on something, right? So when you go to the moon in Apollo 11, what's the first landing on the moon? 11? Yeah. Wasn't it? Yeah. You're not reacting against anything. You're just throwing something out of the bag. It's like out of the bag. And it doesn't have to push on something for you, a continuous stream that links you with the Earth, but just the fact that you're throwing puppies out the back of Apollo 11 means that you're able to change the momentum of what you're throwing out to be able to drive you in the opposite direction. And so this is just an example. I'm not sure. I looked at it very quickly. Oh, it's already gone, I guess. Things that people play around with. I don't know who these guys are. They look like just having a good time. So I don't know how commercial this is or what it is, but exactly. But again, it relates to what we're going to talk about today, and that is conservation of momentum, just following on from last time. Okay. So that's where we start today, and I want to go quite methodically through three different ways of three different problems, I guess, three different geometries. And so the geometries are, we talked about this last time, this is the undershot weir, and I guess we were able to show that if the weir is all the way down and the fluids are static, the forces acting on that weir is larger than if you allow out through the bottom. After you have the solution, it seems kind of intuitive that that would be the case. There'd be less force required. But the other things that we'll talk about are these. I think I'll switch these with each other in order. And we'll talk about the jetpack. We'll talk about a vane. We tried it last time. The vane is a jet of water that's hitting the Pelton wheel, but we can just idealize it as something on runners for this linear conservation of momentum. And then the decapitated cylinder speaks for itself, the sleeping giant. So let's have a recap. So the recap is this. The geometry we have is the same geometry that we've had before. The equations that we get out of it are the ones down here. And it is that if I write this out, this is sum of the forces are equal to this term we don't consider, and it's the sum of velocity times v dot n area times density. And our sign convention is, if I move this up slightly so I've got more space, I'm just going to move this. The sign convention is that we have fluid going in and we have fluid coming out, and we have two terms that we need to take care of. One is the sum of mass flow rates, which is this second part. Which is velocity times area, which is volumetric flow rate, times density, which is a mass flow rate. And that is in steady state. I guess I don't need to write that. So the mass flow rates. So mass flow rate out is positive. Mass flow rate in is negative. And we have this other term for velocity, which is a vector. And it's always in the direction of the coordinate system. Positive in the system. And so if we have x and z, then this would be positive, and this would also be positive. So we have to, so that comes out of this dot product. And so, but for the problems that we'll deal with, you can think of it, we won't use the dot product, we'll just use relative flows. And I guess the other thing that we broached but never actually used, I love my drawing of the fireboat. Don't you love that? Perfect every time. Is that we said that if you have a boat that's moving at a velocity of the control surface, VCS, and you have something that's coming out of the front, which is out of the, perhaps I'll do it just as the gun. So this is squirting out, and this is what we've called the relative velocity W. And then what we can do is we can take the two of those and add the two vectors together, in which case we have the velocity relative to a static observer. VS stands for static. So this stands for someone standing on the quayside and looking at the boat go past at some velocity, squirting out of the front at some velocity. If you look at the bead of water relative to that static observer, it's going at the sum of those two vectors. This is what you would see. You'd see velocity, a bead of water traveling at the sum of these two velocities. And that's important. And that's important because F equals ma, which is what we're using. We're not using anything other than that. The acceleration has to be relative to some coordinate frame. We sit on the planet Earth, static, and everything is moving relative to us. So we can write this equation in terms of these velocities. And so this expression is written in terms of this for now. But we can manipulate it. And what we can manipulate it is that if we take, I guess we should realize that this is a vector, right? X, Y, and Z. And this is a vector, X, Y, and Z. Typically, we'll only choose one of those equations at a time, as you'll see today. But if we are taking this expression and we rewrite it here, I could write it as sum of forces are equal to velocity static times rho v static A. And so it's convenient for us to be able to write this term here as v static. I'm just writing out what we've already said, is the sum of the control surface and the velocity of the water coming out. And so we could, for instance, substitute this into here, and we would end up with a rearranged term, which is the sum of W plus VCS for this term, right? This term here. Density, let me write this as W for reasons that we've talked about before, and the cross-sectional area is equal to the sum of forces. This is this term here is a scalar, right? It's out of this is the mass flow rate, out. And these are both vectors because they have directions. And so we can always write it like this. And so this expression up here is always true. For everything we'll do. And sometimes we have to use it in this system, but we'll look at two classes of problems. The first ones will be steady state. And the last one will be unsteady state. So the gas cylinder has to be unsteady state. It's bleeding gas. It's only got a finite mass of gas in it. So sometimes if you leave it in a long time, there'll be nothing coming out of it. So it's changing all the time. So for this case, as we'll see, we have to use this expression. But for steady state, we can modify this expression, because we know that we could rewrite this expression as sum of forces equals W times mass flow rate plus VCS times mass flow rate. All I'm doing is, this is the mass flow rate term. It's these two components, so I'm just writing them out separately. And this is useful because by definition for steady state, we know that the sum of mass flow rate is equal to 0 by definition, right? Mass in equals mass out, wherever it comes from. So if this is always the case, then if we take this scalar quantity and we multiply it by the velocity of the control surface, every single point on this boat has to be moving at the same velocity of the control surface because it's a rigid boat. The boat isn't deforming. If it was a balloon, that wouldn't be the case. But here, VCS is a constant. So a constant times the sum of mass flow rate. Because mass flow rate equals 0, then multiplying it just by a number will also equal 0. So we can get rid of this term. So for steady state problems, the equation that we solve, which we'll use in a moment, is sum of forces is equal to W m dot. So the two terms are important if we have an unsteady problem, the cylinder problem, but for everything else we'll do today, we can just get by with this relationship. And they are vectors, I guess, right? So, too much theory perhaps. Let's just put the rubber on the road and deal with the problem. So I'm going to do the jetpack one. And so I'm going to have a simplified figure. And I won't put my notes up and move through it quickly. I'll just put this figure up. And what are the components we have acting? Yeah, okay. So we have velocity flowing into it. And I guess I call that V1. And we have velocity coming out of it. Call that V2. And it acts on some area, A2, and this acts on some area, A1. I guess we also have a pressure acting on it. Probably should have done it in a different color. See if I can be fancy here. I tell ya. And so that is, we would think that it's pressure also acting on A1. We could imagine that it's a distribution that has some angle to it, but it's such a small pipe that we probably wouldn't care that it changes. And we have some pressure coming out. And we'll call that P2A2. And I guess the areas are the same. We have a weight of the person, not necessarily a guy, which is mg. We have a coordinate system, which is xy, xz. What else? Yeah. And I suppose what I should have done earlier was that I should have drawn a control surface around this, which I'm trying to do in gray. And the control surface would just include everything we're interested in. And so, I don't know if, yeah, fine. So it could be drawn as this. So this is just the same thing. I'm just drawing the same thing as before. And we're just going to resolve forces. So what can we say about this? Taking too long, right? So I guess I didn't really need to do this. The directions. So we want to know, what would we want to know? We want to know, you want to size a motor, you want to know what velocity you have to drive the fluids out of the system. So what we can do is we can analyze this. And if we do that, it will be forces are equal to velocity times mass flow rate, sum of. We only want to resolve in the vertical direction. We don't really care about what happens horizontally. So it would be sum of the forces. I guess I will take this as a, not a superscript just means resolving in the x direction, not a an exponent. And so what would those forces be? So it would be P1 times A1 would be this force. mg is acting downwards minus mg, minus because it's acting downwards, and this is our positive direction. And this is equal to, first of all, this is going to be a real pressure. This pressure here is going to be 0, right? Because it's atmospheric. Comes out of the jet. The pressure acting horizontally on the jet as it comes out is the atmosphere. And we know that pressures in all directions have to be the same. So this has to be 0. This is not 0. And so we could add that. This is P2, right? Didn't stop me. And actually I'm going to remove this. So if we're resolving horizontally, this force has no direction, no component horizontally, so we don't care about it. And so the only other components we have are the velocities. This velocity is also acting horizontally, and so we don't care about that. It has no component in the direction of x, since we're resolving in x. Not log x, but in x. And this would be this term here. So this would be v2 in the x direction times v2 area times density. This would be x. So v2x times v2x times area times density. That's this term here. And then we just need to figure out what our sign convention is. So velocity 2 is in the downwards direction. So this is negative. Velocity 2 for the control surface is out of the control surface. So this term here is v2a rho. And so this is the mass flow rate. And mass flow rate by our sign convention is positive out of the system, not in the direction of the coordinate systems. So this is plus. And this is 0. And so it would just be equal to minus mg is equal to minus v2x all squared times area 2 times density. And so since these terms both cancel out on either side, make life easy for ourselves, we have v2x squared equals the mass of the person, 100 kilograms if it's me, g divided by a2 density. And if we want to get velocity, we just square root both sides. Which is v. So that's it. And so if we want to be able to solve that, we just have to realize the hardest thing, I think, is setting the problem up. Draw a control volume around it. Everything's inside the control volume. The weight of the person acting downwards, it's being counteracted by the momentum change of the velocity. The puppy's being thrown out of the machine, and there's no pressure acting on the base because it's in the atmosphere. This one is orthogonal to it, so we don't care about it, what's coming across this boundary, and we can solve exactly for what we want. Okay? So that's it. So that's one. Okay? So that's static. We used velocity. We could have used relative to the boundary velocity because they're the same, right? So in this case, v static x is equal to what we would call w x. The relative velocity across the boundary is the same. Okay. All right. Silence. Very quiet today. Let's do a vane problem, just like we did last time. So the idea is that we have a vane. Flow goes into the vane at some velocity and turns a right angle and is forced upwards. It's on a sled, I guess. This sled is on a surface. I won't draw the vane itself. So this is on a sled. Again, we have locations 1 and 2. I'm going to call this W2 A2, and I'm going to call this W1 A1. Area is the cross-sectional area that comes across. I'll remind ourselves of this little fact that if you look at the velocity of the control surface and the velocity of the water coming into that, that is equal to the static velocity. And the static velocity would be the velocity coming out of the hose, right? So this is being driven by squirting. It's squirting, it's hitting the sled, it's going up and being ejected out of it, just like the Pelton wheel. But it's free to either move or not move. And so I guess the other thing that we can add to this is that this could have a velocity of the control surface, which we'll call VCS. And not to get too many colors here. Come on. Control Z. And we could try and restrain it. So I won't draw, actually perhaps I'll do it as a superscript again, Fx. And so if it's free to move, then the force acting is 0 and it will move. And if it's restrained, then this force has to be equal to all the forces that are pushing it to one side. So what we can do is we can go back to use our system as we had it before. We've already said that we can write this system as sum of the forces in the x direction are equal to the sum of the products of velocity, static, and mass flow rate. We already said that we can substitute this with this term here, W plus VCS. And we've already said that if it's steady state, then we can throw this second term away. So I don't think you have to realize that rationale, but you can realize that if it's steady state, then the term that we can use is that the sum of forces in the x, in whatever direction, are equal to the sum of W x times mass flow rate. Yeah, okay. So let's itemize all the components we have. So we have forces would be force in the x direction. We didn't draw a coordinate system, but let's. We're going to resolve only in x, because that's all we're interested in. We're interested in calculating what this is. So this force in this orientation would be minus F. And we're going to calculate what these individual terms are. And so we could also write this equation here as W times area times density, right? That's what mass flow rate is. And so let's write it out here. Wx of 0.1 multiply, and it has a sign to it, which we'll come back to, multiplied by Wx of 0.1, this term here, times area times density, area 1, And we're going to add to that this term here, which would be W2 in the x direction, because we're resolving an x, multiplied by W2 times area times density. This term is the mass flow rate out, right? So this is W2 in the z direction, right? You could just think of this as m dot, but the mass flow rate is W2 in the z direction, which I guess this would be, and W2 in the x direction is 0, right? The vector, the component of that vector, if it was canted over, it would have a small amount here and a larger amount vertically, but if it's vertically, then W2x on this is 0. And so if that's 0, then this is 0. It has no sign, I guess, but this one would have, it's out of the control volume, so it'd be positive. So this term is lost. And then we can go back to this. So what's this? This is a mass flow rate in, which is negative. So this is the mass flow rate term here. A1 times density times this. So this term would be positive by definition. Negative. Flow rate in is negative, and flow rate out is positive. And it's in the x direction, so this would also be positive. So this is, if we take that, well, I won't do that, just write it out. So the force in the x direction that we have to apply is equal to W1 in the x direction times mass flow rate, which I'm going to write as squared, because we have two of them, and an area 1 times a density. So this is saying that the force that's applied is proportional to the velocity into the system squared and the area and density. So this is MA, F equals MA, essentially. And so we need to know something about the velocity that it's influent. So it's coming in at the jet velocity Vs. So what we could do is we could use this expression again, and we could write that Wx is equal to so the sum of these two is Vs minus, so this W plus Vcs equals V static. So W is equal to Vs minus Vcs. And so we can substitute this in here. And then everything becomes apparent. So the force we have that is applied is equal to the static velocity, which is how it comes out of the hose, minus the velocity of the control surface, multiplied by the area 1 and the density of the fluid. So if it's water, it's 1,000 kilograms. And so there are two end-member behaviors, as we talked about yesterday, that are perhaps important to us. Not yesterday, Monday. Man, we went through a lot. We talked about when the velocity of the control surface is 0, the forces are maximum. When the velocity of the control surface equals the velocity of the incoming jet, then it's equal to 0. And that's exactly apparent in this expression here, in that there are two conditions where you can get it either to be a maximum or a minimum. So this is controlled. This is going to be our 1 meter a second. So if we allow the control surface to go at 1 meter a second while it's being squirted in at 1 meter a second, then, so if VCS is equal to the velocity from the hose, then by definition, the force you need to hold it is equal to 0. Alternatively, if VCS is equal to 0, then you're holding it static, and that's going to be the maximum force that's hitting the sled, and then the force would actually be Fx is equal to, this is squared, right? Is equal to Vs squared A1 rho. And so those are two key results because they say exactly about the amount of power that's in this system. So if we take power to be equal to force times velocity, so that is newtons times meters a second, which is a newton meter is a joule, and a second, and this is a watt, after James Watt and his steam engine. Then you can do the same as we did before, and that is that if you draw velocity of the control surface and velocity of the control surface, obviously that's a line of 1 to 1. If you draw the magnitude of the force, F sub Fx, then when the velocity of the control surface is 0, then it's maximum. It's this value here. When the velocity of the control surface is equal to the incoming jet, then that gives you the minimum force. And if you plot power that would be generated, this is all VCS and VCS, and this would be power, which would be the product of these two, right? Call it power, not P. Then this times 0 is 0. This times 0 times big number is also 0. And so if you look at the median location here, where this is finite and this is finite, then the power would look like this. Something like that, right? You could calculate what it would be by choosing those things. We haven't done this calculation in the middle, but it has to, take my word that it has to go not necessarily linearly, but controlled. It won't be linearly, actually, because it's a function of v squared. So it won't be linear, but you get the idea. So you have to provide some resistance to it. You have the Pelton wheel swinging, and you have nothing coupled to it. You can't generate any electricity. You have the Pelton wheel static, so the motor is stalled. You're not generating any electricity. But the sweet spot is somewhere in between here, where you're allowing it to move, and it's moving the armature through the magnets and generating electricity as a result. Okay? Yeah.
Why is VCS, for the first graph, why is VCS both the X and Y?
Because I chose it to be. I guess one of them could be V static, right? Well, so yeah, I can do that because I want to. No other reason. It has to be a slope of 1, right? And I guess one of these could be substituted with, I guess this is, yeah, perhaps this is, because Vs is the same in all of them. So I guess this would also be, I've chosen it to be that. And so when the velocity of the control surface is 0, then this is the right term. When the velocity of the control surface is equal to the velocity of the static jet, I guess you could substitute one of these by the static velocity of the fluid coming in. I'm not sure which one, but for me it makes some sense. Okay. Right? Final one. Decapitated So both of these, I guess, just to go back to the top, both of these have been steady state. And so we could always use this only, because the velocity of the control surface cancels out because of the logic we gave here. If we do the decapitated cylinder, it's no longer steady state, it's unsteady, so you have to use this full form. So let's do the cylinder. Okay. So we got Mythbusters. Let's see what shape it will do. Oh, not bad. So this is our gas cylinder. Oh, it's pretty good. And we're going to cut the head off it. And we're going to have, I'll call this W2A2 and P2. And in here, I'll call this one. A1, no, doesn't need A1. V1, P1. So this is the pressure inside the cylinder. This is the velocity it comes out of. We know that the equation we want to use is sum of the forces are equal to W plus VCS multiplied by W area density, right? So this term here is mass flow rate. We're interested in what force we have to apply to it. We'll have a velocity of the control surface. We'll have XY coordinate systems, XZ coordinate systems. And we'll apply force to it to stop it from moving. I just call it F. And in this direction. And so we can figure out exactly what the terms are for this expression. First of all, we have to know, we don't know what the velocity it's coming out at is. And so we could write Bernoulli. I think we did an example in one of the videos you'd have watched with an example like this. And so it would be P1 over gamma plus Z1 plus V1 squared over 2G plus P2, not plus, equals P2 over unit weight plus elevation Z2 plus V2 squared over 2G. If we do it on a horizontal surface, then Z1 and Z2 are the same. So we lose it, right? Just moving on this horizontal surface. P1 we need to know. There's no velocity in here because it's stagnant, right? It's static. So this will be 0. And once it comes out here into the atmosphere, because pressures acting on the side of the jet are atmospheric, 0, then it has to be 0 in the jet as well. So this has to be 0. So we have V2 squared equals P1 over rho G times 2G. So that would give us this. And so the square root of this would give us the velocity. So take square roots on both sides, I guess. I'm not going to use any numbers in these, but you could do if you wished. Right? So we have V2, and then we can do the rest of our relationship with this. How are we doing? Time. 8 minutes. So, sum of forces. So we have F, X, positive, as we show the direction here, is equal to Wx of 2 plus Vcs in x multiplied by W2 in x area of the nozzle times the density of the gas coming out. And so we have individual components there. We'll keep it written as this and decide what those individual terms are. I guess I should have left myself some more space because I want to do the signs of these. VCS we don't know, so we'll just take that as positive, and by definition it's positive in the positive direction here, so it should be positive. W2 in the x direction is in the x direction, so this would be positive as well. Can I do this? Does it change it? So this we said was positive. This would be positive as well. And this is coming out of the system, so this would be positive as well. So all of these terms are positive. And so from that, we can merely write the fact that the force that we'll apply is going to be equal to W2 in the x direction, which is what V2 is, plus velocity of the control surface, also in the x direction. It's the only direction it can travel because it's on a flat surface, and multiplied by W2x area density. And so we can get two conditions out of this. Holding it static, where we don't get any work, but there'll be a maximum force, and allowing it to go at its own speed when the force will be zero and is not being restrained. So if the force is equal to zero, then the only way this force can be equal to zero, because W, I guess we should also make the case that W2x is equal to the velocity coming out of this thing, right, that we just calculated by Bernoulli. Bernoulli is calculated in this reference frame, so if this is the rate at which it's squirting out, which by definition is W2. So the only way this can be zero, if this is finite, is if W2 is equal to minus VCS. If the two terms here give us zero. And that only happens when this is. So in other words, it will only be no force applied if it's squirting out at W2 and it's going off to the opposite direction at velocity W2, which is this control surface. It's exactly the same as the vein, right? If you're squirting fluid into here and there's no force applied, the vein will be moving at the velocity of that bead of water, which is right at the front of it. It's trying to get away from it, you can think of it. And so there's no force applied. So this is exactly the same. The other condition would be when the force in the x direction is maximum. And that will be maximum when this is equal to zero. Right? Perhaps I won't mess it up by doing that. So by definition, VCS equals zero. And then the magnitude of that force would be F equals W2x all squared times area times density. That's it. And it's again, the observation that it moves really at the rate at which the stuff is coming out. That's been a kind of common theme in this case, right? In the vein case, the velocity at which it's coming in, which is the influent velocity plus the control surface, which is just really the jet velocity that's coming out of the hose. So this is moving to the right to keep ahead of the furthest bead out of the hose. And if it's doing that, then the force that's being applied on it is zero because it's on frictionless wheels and it's running. If you stop it from moving, then that generates the maximum force, and we can calculate what that force is. So we can calculate those. The utility to us would be that if we can calculate the force that's applied when it's held static and also when it's allowed to run at its own rate, then we can also calculate it if we hold it at VCS over 2 or VCS over 4. And we can calculate what each of these forces would be. And we could also calculate the power curve that we get out of it, because we're changing linear kinetic energy into kind of rotational momentum, if you think about it. And we'll talk about that tomorrow, Friday. And the same theme is here. The at-rest velocity that this would move at to the left, so it's coming out at velocity w2, it's moving in the opposite direction to this at that same velocity. So it's moving in this direction at w2. That's all it's saying. And you just have to keep, doesn't matter what sign convention you use. We could have written the force being in the other direction, in which it would have come out with a solution that the force would be negative, so it would correct for that. And so I guess the key is to be able to draw these little diagrams and try to understand what's going on. We also put this equal to 0, right? Because we know this is atmospheric. So, okay? So you have a record of those. So this is about as straightforwardly as I can show them. And that gets a bit complicated. So I guess as a parting shot, you just need to remember, why don't I write it out? So steady state. You can always use sum of forces is equal to W times W rho area. Unsteady, you have to use W plus VCS times W rho A. So this was our decapitated cylinder. This was our vane. Zip. So these are the expressions we used. And you can always resubstitute as you wish that the static velocity is equal to the velocity of the control surface plus W, the velocity coming from our boat. Not such a good boat there. VCS, W, BS. It's merely a statement of that. And so it just takes a little bit of manipulation. So that's the summary. Don't need to worry about the derivations. And I guess the other thing you need to be cognizant of is our sign convention. I could copy it from above, but it's probably worthwhile writing. So when we do the mass flow rates, then positive is out, in is negative, and if we look at either V or W or VCS, I guess not VCS, right? Either of these, this is positive and this is positive, right, for our coordinate system. So that's what we've talked about for the last week and a half now, right? Mass flow rates have the same convention, and we use the same convention here. And the external velocities we have to do relative to the Cartesian coordinates. And so there is on the Wednesday midterm a linear momentum question. So you know that, right? The stuff's posted. Yep, Nicholas. Yes? A week when, 2 weeks today. Or that week, the one on Wednesday. The review video is posted. It was in the email on Friday. Monday is free jets. Wednesday is linear momentum. And Friday is rotational momentum, which we'll talk about tomorrow, Friday. I hate to bring it up because it's such a sobering, you've all gone so quiet, such a sobering comment, but it's out there early so you can, this is the stuff. We've covered everything you need today for Wednesday.